Welcome to the ninth episode of our series, The Mother Earth. The data obtained through space missions have revealed that the cores of Jupiter and Saturn may consist of metallic, solid, and liquid phases of hydrogen and helium, Fe-Ni silicates, enveloped by the huge mass of gaseous matter extending up to their surfaces. Jovian planets are hot inside, though their surfaces are freezing. Jupiter's temperature increases from about minus 145 degrees centigrade at its surface to a very high, nearly 25,000 degrees centigrade at its center. In Saturn, it increases speedily from minus 178 degrees centigrade to about 8,400 degrees centigrade in its central region. What does it indicate? It indicates that the heat generated inside these gaseous giants is far greater than the heat received from the sun. Compared to the temperatures in the cores of these two gaseous giants, the temperature estimated within the Earth's core grades from about 3,500 to 6,000 degrees centigrade only. These appraisals have been based on seismological deductions and are supported by the data obtained on melting points of materials like iron-nickel alloys, iron sulfides, iron copper sulfides, and iron magnesium-rich silicates. Since the Earth's core is dominated with the two elements iron and nickel present as alloys and sulfides, its composition is considered akin to that of the iron meteorites. It is possible that the presence of higher contents of sulfides of iron and nickel and copper in the outer core should be one of the factors that lowered the melting points of the matter constituting it and maintaining it in a fluid state. Since it is also supposed that the silicate minerals constituting the Earth's lower mantle may resemble those of the HED meteorites and the achondrites, experimental results on the melting points of the FeMg silicate minerals were also very useful in assessing the heat inside. It was revealed from these experiments that in the FeMg silicate minerals, the densities increase with higher Fe content, but their melting points are lowered. That also provided a cue towards understanding the transition of matter in the lower mantle to a fluid state in the outer core. During melting, the matter expands, its volume increases, isn't it? Melts are in equilibrium with solids at atmospheric pressure conditions. But when subjected to very high pressure conditions, the matter contracts, gets a more compact morphology, which reduces the volume. The density of matter increases in such high pressure conditions. The minerals of the Earth's lower mantle perhaps had to undergo changes in their crystal structures first and then finally melt. It was around 1914, that is, in the second decade of the 20th century, that the Gutenberg discontinuity between the Earth's mantle and the core was identified at about 2,900 kilometers depth from the Earth's surface. It is a seismic discontinuity named after Benno Gutenberg, the German seismologist who proposed it. By 1974, about 60 years later, as the field of seismology was further improved and refined, the trends of the two major earthquake waves, that is the P wave, primary wave, and S wave, secondary wave, were more precisely determined, and their travel paths inside the Earth were mapped and computerized. Professor Francis Birch and his colleagues at the University of California, Berkeley, showed that alpha, the P wave velocity that steeply rose in the Earth's mantle, first got subdued at the Gutenberg discontinuity, but rose again thereafter, though gently, up to a depth of about 5,145 kilometers. Beyond that depth, alpha showed a sudden rise and continued its upward trend steadily up to the center of the Earth. The velocity of the S waves, denoted by the symbol beta, also got subdued at that depth, but surprisingly, its trace disappeared totally beyond the Gutenberg discontinuity, that is, in the outer core. The value of beta becoming zero betrayed that the matter in the outer core has very little rigidity or no rigidity, and thus it confirmed the liquid or fluid physical state of the outer core. Such melts or fluids can attain a solid state again if subjected to still higher pressure. We know that the melting point of matter rises when subjected to high pressure. The continuous rise in the pressure within the Earth's inner core prevents the solid matter inside from melting again. The S wave velocity, which became zero in the outer core, was traced again, along with, of course, the uninterrupted P wave velocity at depths of about 5,145 kilometers from Earth's surface. That confirmed that the matter, which was fluid in the outer core, gained again its rigidity, pointing towards the Earth's solid inner core. This re-emergence of the S wave delineated another seismic discontinuity referred to as the Lehmann discontinuity, named after the Danish seismologist Inge Lehmann, who inferred it. This discontinuity is not as distinctly marked as the Gutenberg discontinuity. The plausible reason is that the separation of the inner core from the outer core was relatively a slow process. It involved a gradual phase transformation of matter from liquid to solid state. The temperature across this discontinuity is estimated to be in the range of 5,400 to 6,000 degrees centigrade, and the pressure in the range of 330 to 360 gigapascals, 1 gigapascal is equal to 10 kilobars. In such PT conditions, very high PT conditions, the elements Fe, Ni preferred a more compact solid crystal structure whose melting point was higher than the temperatures that were reached in the outer core. The seismological data provides evidence indicating that the matter in the outer core from 5145 kilometers up to 2900 kilometers, that is above this discontinuity, is about 8% less dense, less viscous than that in the inner core, ranging from 5145 kilometers to the center of the Earth. The deducted density of matter betrays a sudden rise from 5.5 to 9.0 grams per cc at the mantle core boundary, that is the Gutenberg discontinuity, but shows a relatively gentler and smaller rise from 12 to 13.5 grams per cc at the outer core inner core boundary, that is the Lehmann discontinuity. The Earth's core acquired such internal structure during the initial years of melting and gravity separation. Because of that, if you recall, it acquired a strong magnetic field. For this process of initial melting, the principal driving agency was the sustained heat energy inside. What could be the source of heat? In every planetary body that underwent such igneous process of melting, it must have been similar. Was the kinetic energy released during the gravitational compression or collapse the only source of heat? That, of course, has been an important feature of planet formation from a nebular mass. Another source of heat would be the exothermic reactions during the frequent and speedy impacts of asteroids and comets in the Earth's nebula. That added physical heterogeneity also to the process of accretion. The third and the most important source of heat would be the heat generated during the radioactive decay of short-lived isotopes like aluminum-26, palladium-107, and iodine-129. Jean-Ali Barrard, in a recent paper of March 21, attributes the heat generated by radiogenic disintegration in the aluminum-26, magnesium-26 system for initiation of melting in the chondritic nebular mass that gave rise to the andesitic achondrites that were found in Algeria. Detected in the compositions of the meteorite matter, such short-lived isotope systems have been useful time indicators also, predicting the earliest process of igneous crystallization in the solar system. The heat generated by the radiogenic decay of long-living isotopes like uranium-238, thorium-232, and potassium-40 has largely sustained the present internal structure of the Earth. The heat generated has progressively decreased, however, with time that lapsed since the Earth established itself as a protoplanet in the solar system. Roughly twice as much heat was generated in the first 2 billion years history of the planet, that is, from 4.55 to 2.5 billion years. What have we learned in this episode? We have learned that there were three sources of heat generated inside the Earth's nebula, which were responsible for the melting and gravitational separation of the Earth's core from its mantle. How the difference in temperature regimes and the compositions have kept the outer core in fluid physical state. How the P-wave velocity alpha showed a rapid increase in entering the fluid but denser medium of the outer core. How the S-wave velocity beta disappears in the fluid medium of the outer core but re-emerges as the matter gains rigidity. How the increased pressure regimes transform the inner core material into a solid physical state. In the next episode, we will look into the magnetic field of the Earth and the composition and physical state of matter constituting the Earth's upper mantle. Thank you very much.